We know that electric field strength E is equal to the force on a small positive test charge divided by the number of coulombs in the test charge. So let's say you walk into a room and you decide, I'm going to measure the electric field in that room. Here you are, and you've got your test charge handy. When you get inside, what do you find? There's a giant positively charged sphere in the middle of the room. And you say, I wonder what the electric field looks like around this sphere. So you walk up to the positively charged sphere and you place your positive test charge. They're both positive, so the test charge feels a giant repulsive force. If you want to turn the force into the electric field strength, you have to divide by Q the charge of the test charge. Well, let's pretend that your test charge has 2 coulombs. If you divide the force in half, then the arrow will only be twice as long. So the electric field strength E looks like that. It points in the same direction as the force. And then you move over to this location, and you place your test charge here. It feels a huge repulsive force. To turn the force into the electric field strength, we divide by the test charge Q. And you do this moving around from point to point. You always measure the force on the test charge. Then you divide that force by Q to get the electric field strength. After making it all the way around, you move to this point, a little farther away. What happens to the force on the test charge? Well, we know the Coulomb force is equal to a constant times the product of the charges divided by the distance squared. When you increase the distance of separation, you increase the denominator, and that lowers the force. So when you put your test charge farther away, it doesn't feel as strong a repulsive force. Again, to turn the force into electric field strength, you divide by Q. And now the E arrow is half as long. If you go around from place to place and you do this again, you find a weaker force, and so a weaker E vector. After making it all the way around, here's what the space looks like. To recap, we put our test charge here, we measured the force, and we divided by Q to get the field strength. We did this at every point. And then we went farther out, and we found as you increase the distance, the force decreases. So the electric field decreases as well. We don't often draw arrows like this. What we can do instead is connect all of the arrows together as solid lines. These are called field lines, and they show you where the electric field points. If you were to come in and place your test charge right here, that positive test charge would be pushed along the direction of the field line. The field lines don't extend inside the charge. The reason is because the electric field is 0. If you put your test charge, inside, it would not feel any force at all. It kind of is insulated in a way from the electric field. If it had been a negative charge instead, the only difference is that the field lines would point in. Because if you were to have taken your test charge, which is always positive, it would have been attracted with a force like this. So you divide the force by Q, and the electric field strength, E, would point in as well. Whenever you have a positively charged sphere or a negatively charged sphere, or even just a point charge, there's an important equation we can derive. Imagine taking your test charge and placing it at some distance r from the center of the source. We know exactly how big this force is. It's K times Q test times how much charge is on the sphere, big Q, divided by the distance squared. But if we take this equation and replace the force up top with this big expression, what do we get? K times Q test times big Q over r squared, all divided by the test charge, Q. So the test charge cancels out, and the electric field strength due to a single source charge, like a big sphere, is K, Q over r squared.